project. It's called Illness Prevention, Anomaly Detection in Body Vitals. The motivation for this project is the insane amount of chronic death diseases in America. So every year, many people die from heart disease, lung cancer, stroke, diabetes, and kidney disease. Actually, these diseases are detectable in early stages, which means if you monitor your body vitals, if you measure your blood pressure every day, if you measure your glucose level every day, you can have a rough picture of how likely you're exposed to these diseases. Well, this project aims to formalize this approach and try to draw some conclusions from your bodily vitals to suggest if you do have the risk of certain chronic disease. Okay, so this project has two phases. The first one is anomaly detection. Basically, everybody has a different set of personal data, and we want to ensure that the anomaly we detected from your data is an actually anomaly for you. We'll see what that means in a short while. And if our algorithm determines that, yes, you have an anomaly today, then we would effectively translate that anomaly signal into possible disease or illness that you might have. This is based on the Bayesian network that we'll discuss in just a second. All right, so the anomaly detection is based on something called a personalized distribution. Basically, what is your very own personal distribution? This tells a lot about what counts as an anomaly for you. For example, if I have an average of 110 level of blood pressure every day, that might be normal for me. That might be my average. But that may, in the public data set, occur to be a very, very high blood pressure and count as an anomaly, although it's just, normal. So we want to infer your anomaly based on your everyday measure of your normal data. That means our algorithm would take in one file, would take in a file that looks something like, this. It means in every line, we have a daily measure of blood pressure and then glucose level. So what's your everyday measure of blood pressure and glucose level? We could infer from this data. And this is just a dummy txt. But what we can infer from this txt is your daily distribution of, say, every day, what's your blood pressure level, what's your glucose level, and then we can infer from, for example, today's data. If I have 120 and let's say 130, this would be an anomaly for me because 120 is maybe significantly higher than 110 because I have a very small standard deviation here. So this is counted as anomaly, definitely. And 130, wow, that's well above my average. That definitely does count as an anomaly. This is just a little demonstration of what personalized distribution would mean for anomaly detection. And now we have the second stage, when we actually arrive at some significant anomaly signals in the previous stage. Say, oh, I have a very high blood pressure level. What does that mean for me? So we do construct a Bayesian network of how strong each symptom correlates with each chronic disease. In this very simple diagram I draw myself, it basically says for each of the anomaly occurrences, for example, there's a very strong blood pressure anomaly. How does that correlate to my heart disease? And if I do have a concurrent very high glucose level, what does that mean for my prediction of my heart disease? So for stroke, we also draw our conclusion from both the blood pressure level and the glucose level. So it's a two-way distribution. And so how do we compute this essentially probability of having heart disease given that you have exhibited anomaly in blood pressure and glucose level? This is just one formula we are interested in, namely how many occurrences during our data sets that suggest that heart disease appear with the accompany of anomaly in both blood pressure and glucose level. So we could just do a brute force scan of all our data set of our cardiovascular disease and evaluate how many occurrences do we have that has heart disease and has these anomaly occurrences versus what are all the counts of the anomaly occurrences. That way we could arrive at a final conclusion of what things are like. What's the probability of heart disease given that you exhibited these anomalies? So, like I said, that's just one value we're interested in. We're actually interested in 16 different values. Namely, like if you exhibit any combination of anomalies, do you have one anomaly, the other anomaly, or no anomaly, or both anomaly? That would give you a rough count of like how risky you are to a blood pressure disease. So I'll just breeze through some of the example here. Okay, so from the anomaly detection stage, say we did detect both anomalies in blood pressure and glucose level. Wow, that's bad news. But how bad is that? Well, we would have to look at the signal translation stage to infer four values we're interested in. Namely, the probability that we have heart disease in our current situation, or the probability that we have stroke in our current situation, or just we have diabetes or kidney disease in our current situations. And we extract these values to infer, to like tell our user, okay, so you have 90% of probability to have a heart attack. I'm so sorry. Okay, so that's a brief introduction, and I'll just walk through some code in case we do have time. Yes, I'm going to walk through this really quickly. We have 5 functions. The first one corresponds to the anomaly detection. It's called read subject. It takes in a distribution of what your normal measures are and what your today's measures are. And basically using some of the fancy calculations of mean and variances, and we do arrive at a result. The first entry of that result tells you if you do have anomaly in blood pressure, and the second entry tells you if you have anomaly in glucose level. And this result is passed into four of our functions that evaluate cardiovascular risks, stroke risk, kidney risk, and our diabetes risks. So in each function, we did some fancy calculations. Basically, it's just counting up all instances of anomalies in blood pressure and glucose level. We define anomaly in blood pressure here by this formula, which is if you have obtained an average between your high blood pressure level and your low blood pressure level, the average between them dictates your actual blood level is. And how does that blood level compare to your mean and standard deviation? If that does have a very great advantage in terms of your mean and distribution, that means you have anomaly. That means you have anomaly in your blood distribution. And yeah, basically it just tells you, okay, you can count this as an anomaly. So we count together all the occurrences, and then we would return basically the full values we're interested in. So that works for everything. And like during an everyday test, we just basically read in a subject with proper distribution and everyday and today's measure. And we determine, okay, if your anomaly situation is this, and we should give you an explanation over this certain subset of probability. So this is a brief summary of our project. Thank you, and welcome to the future of illness prevention.